Okay, so for particles that we wouldn't call quantum particles, normal particles, particles that are much larger, much heavier, much more massive than photons, which have no mass, electrons, and other sort of subatomic particles. Um, Particles that are normal size have, like bullets, they have wavelengths which are incredibly small. And so they in fact do interfere. There is an interference pattern because they do have wave-like properties. But since the wavelength is incredibly small, and by incredibly small I mean small, so small that we can't really, with any experiment or any experiment that we can do at the moment, we can't actually, we have no way of measuring the interference fringes. We have no way of measuring the wiggles, because in some sense the pixels on our detector, the size of our detector, is much bigger, spans several of these wiggles. And so what it's going to measure is the average over several wiggles. And when you do that, when you measure the average of this, right, then what you're going to get is something very smooth, which looks exactly like this. Okay, and so this is why for normal particles, normal sized particles, we don't observe interference effects, because these interference effects are essentially, this graininess, this wiggliness, is essentially smoothed out by our inability to detect variations on such a small scale. Okay, so we're going to discuss, this is a good segue into the next lecture, because in the next lecture we'll be discussing the de Broglie hypothesis that relates the momentum of a particle, any particle, to which allows us to calculate a wavelength, a quantum wavelength, in the same way that an electron has a wavelength, as we showed with the double slit experiment. So we'll learn how to calculate, how to compute, and how to think about the wavelength of any particle, and then we'll be able to calculate the wavelength for normal sized particles like a bullet, and see indeed that it's very, very small.